Our buffers are weak acid, weak base. Some mixtures. And we're going to have significant quantities of both present. So we need both in significant quantities. And one of the most desirable or useful properties of buffers is they maintain a fairly stable pH. They maintain a fairly stable pH because there's acid here, there's base here, and if we add strong acid or strong base, then the pH changes a little bit, but not so significantly compared to water. And so let's take a look at the different types. We could have a weak acid, weak base combo that's not related, and that's going to mean the calculation is very difficult. And so the weak acid and weak base not related. And when I say not related by common ion, other than hydronium and hydroxide. So, this one is difficult. This one we need simultaneous. So, and I think we're looking at the example of acetic acid and ammonia. Is that right? Acetic acid, ammonia. With acetic acid and ammonia, how far did we get in that calculation? That was at the lab also. For the lab, we did acetic acid and sodium acetate. Acetic acid and sodium acetate are a little different for the buffer, because those two species are related. Acetate. So example, we looked at acetic acid. I think, and ammonia. I think we looked at the reaction between acetic acid and ammonia, and then we tried to figure out the pH. Is that right? Does somebody have it in their notes? How far did we get?
We just started when we talked about base strength values.
Okay, and we just got the Ka. We did the reaction, right? And we were looking at the Kb.
No.
We didn't do the reaction? Okay. All right, we'll do the reaction here. Usually in chapter 17, we're going to follow this one, problem-solving strategy or approach, and that is we always react the strongest acid with the strongest base present. And so, did we figure out the K for this equation? Did we do the K value for this equation? Do you have something for the K?
I think we had under root 32.4, and then we solved for x and we got 0.0850.
0.0850?
Yeah.
but that, I think that seems a little small for this one. Which equations did we add up? Did we add up some? And so here, did we use Hess's law? No? Alright. Alright, so we have an unknown K value here. There are different ways of getting it. I thought somebody mentioned one way of getting it
Delta G.
is by delta G, yeah. And then there's another way of getting it, and that was, we could use delta G to get it, because this type of data is in appendix D. We can find out all the delta G's of formation of all these species here. And then we could go e to the minus delta G over RT using appendix D data. But we want, we want more ways. What are the other ways we could determine that? Because, the more ways we know, then, for example, if we aren't given the appendix D data with the delta G's of formation, we might have to use an alternate way. And so what's an alternate way that we can do? And so, I'm not sure what you have in your notes, but I thought we started the Hess's law. I thought we finished the Hess's law. But, no? We did? Okay. We started and we finished and we figured out the K value for this is yeah, that sounds more like it. It was a little bigger, 32.4. And then what we did was we solved the ice, correct? We solved the ice, and then, because initially it was 0.10 molar, 0.10. I'm not sure, this often happens. This often happens that, I was reading something over the weekend, and I was reading that, well, this was for just regular lectures where there's no, they don't write anything on the board and there's no visual presentation, but just an oral lecture. And they did some kind of study where they said that only 10% of the information was remembered. But writing stuff down definitely will increase that percentage significantly. Can you just, what was the E here? Do you have that?
0.10 minus x.
Okay, did we calculate it or we didn't calculate it?
We did. It was 0.015.
0.015. So it was about 85% reaction. Right? Okay, now the question is, what is the pH of this? Is the pH 7 because we have equal amounts of acid and base? Is the pH going to be 7? If I have equal amounts of acid and base, they should neutralize each other. And it should become a neutral solution, but that's not the case. For strong acids and strong for strong acids and strong bases, that would be the case. You have a strong acid and strong base. Because of the leveling effect, that they're going to be equivalent in water. But here we have a weak acid and a weak base, and it depends on, are they equal and opposite? In this case, actually, they are. This is, pH is going to be very close to 7. But sometimes they aren't, These are, because the Ka for acetic acid is 1.8 times 10 to the minus 5. The Kb for ammonia is 1.8 times 10 to the minus 5. So this happens to be equal and opposite, but they aren't always like that. Well, if they're equal and opposite, then should the pH be 7? Yeah, you would expect the pH to be very close to 7. Let's calculate the pH. How would you calculate the pH? Okay, this is, I think, where we left off. Is this where we left off?
Yeah.
Yes. In fact, I know this is where we left off, but I just want to see where you guys are at, if you guys got this down. And so The next step is, okay, so we took the strongest acid and the strongest base, right? And this is what we get. And so what we should do is we should take the next strongest acid and the next strongest base, or, well, we still have some strong acid left over. We still have acetic acid left over. And what does acetic acid do? Well, it can react with the base, ammonia. Ammonia is the strongest base present. What's the next strongest base present? Well, we have acetic acid, ammonia, and one other thing, the solvent. The solvent in this water can act as an acid or base. So the next strongest base, the ammonia and acetic acid can react with would be water. So let's go ahead and take this. So what we should do is we should do this. We'll take the acetic acid that's left over and react that with some water to form hydronium and acetate. Oh, here, I can get my pH from this, correct? I can just stop here and have my pH. No, but if I have an acid solution, I should look for all the hydronium producers. What are the hydronium producers here? Well, I have acetic acid, I have, what else? I have water, and I have one more hydronium producer in addition to water, which is, I have one more hydronium ion producer that's even stronger than water. Water is 10 to the minus 14. This one's a bit stronger, and that is ammonium. Well, look at ammonium. Ammonium's 10 to the minus 10, so I would expect ammonium to also produce hydronium. And I have water. So I would have 3 hydronium ion producers here. And so what would I try to do? I would try to do this stepwise, right? I'll try to do it stepwise and then see what happens. But then again, you know, I have this hydronium from these 3 hydronium ion producers, but I also have ammonia. Ammonia is a base, and bases hydrolyze water to produce hydroxide. And so I got this ammonia here. And, that's going to hydrolyze water to produce hydroxide. In fact, maybe I should look at all the hydroxide ion producers. There's another hydroxide ion producer, and that's acetate. Acetate's a weak base, and that can produce hydroxide as well. So we'll form acetic acid and hydroxide. And then I have one more, water. So what should I do in this case? What I should do in this case is maybe run through the series of hydronium ion producers, run through the series of hydroxide ion producers, right? Because all these collisions are happening. Can you stop these collisions from happening? No. I mean, these are going to be colliding. You recall the Boltzmann distribution. You're going to have enough, kinetic energy at room temperature to the small fraction of these molecules can collide. Well, anyway, so looking at this, I have 6 more ice tables to solve. Is that correct? Do I have 6 more ice tables to solve, and then maybe generate the hydronium, and then generate the hydroxide, and then cancel them out, or something like that? Well, it turns out, if I look at this, there's a bit of... If I look at this first equation here, this first equation describes the equilibrium between what and what? Yeah, and then compared to the second one here, the second one here on this right side describes the equilibrium between
Same thing.
same thing. The only difference between this equation and that equation is what?
Maybe we'll give it hydroxide.
Right, one describes in terms of pH, the other describes it in terms of pOH. The same can be said about this one and that one, ammonium and ammonia, and water. We don't have to do 6. We either do the left 3 or the right 3, it doesn't matter which one we do. Since we're interested in pH, we probably prefer to do the right 3 in this case. Basically, when we go through it, the stepwise, it doesn't work, the stepwise fails, and we end up having to do this simultaneous. Therefore, when we have a weak acid and a weak base that aren't related, it's going to end up being simultaneous. The only thing we can do is qualitative. Therefore, we just solve these qualitatively. Qualitative means it depends on the acid and it depends on the base. If the Ka for the acid versus the Kb for the base, if the Ka is greater than the Kb, then the pH is less than 7. If the Ka of the acid is approximately equal to the Kb of the base, then the pH is approximately 7. And if the Ka is smaller than the Kb, then more hydroxide is produced and the pH should be greater than 7. But figuring out exactly what that pH is a challenging problem. And so since these are redundant, we don't have to do this, since they describe the same equilibrium that we had over there. That's weak acid, weak base. We have to do those simultaneous. And the math for simultaneous is pretty tough because we looked at the math, this is solving 3 equilibria simultaneously because the equilibrium concentration of hydronium has to be the same for all 3. And so the math gets difficult, right? We did 2 equilibria simultaneously and we didn't even finish the math. We just gave up, basically. And so this math is difficult. And so basically you just have to be able to do a qualitative prediction. Well, the Ka and the Kb are pretty, I didn't say they're exactly the same. I said they're the same as 2 sig figs. So the pH is close to 7. All right. We'll do next is we'll look at a special buffer system in which the acid and the base are related. And so if the weak acid and the weak base are related, that is, they're conjugates of each other, then it's easy. These are called Henderson-Hasselbalch buffers. And so since it's easy, that's what we're going to spend all our time on, our Henderson-Hasselbalch buffers. They're easy compared to this. This is difficult. So Henderson-Hasselbalch, what makes them easy? So let's look at the buffer we did yesterday. We tried to do this. We tried to take acetic acid and sodium acetate. I'm going to abbreviate the acetate ion, AC. I don't have to write it all out each time. But acetic acid and sodium acetate, we need these both in significant concentrations. And so let's make this 0.10 molar and 0.10 molar here. And so we have an acid-base mixture. That both, if one species is present in negligible quantities, then it's not a buffer. Let's say if I have an acetic acid and a negligible amount of acetate, then we would say it's an acid solution. In fact, when we do hydrolysis, know, it forms some acetate, but we wouldn't call it a buffer. You know, buffer would have to have significant quantities. And the same thing if we just had sodium acetate, that's a base solution. Sodium acetate will hydrolyze water to form acetic acid, but that amount is small. And therefore, we need both in significant quantities, and this, because it has a certain action that it has. And so we do all the chapter 17 problems the same. The strategy, what was the strategy that we're going to use for chapter 17? You just take the strongest. We always do this for, I think I do this for every single problem. Take the strongest acid plus the strongest base. So the strongest acid presence, acetic acid, the strongest base presence, sodium acetate. So acetic acid plus sodium acetate yields sodium acetate plus acetic acid. And so essentially NR, there's going to be no reaction even to expect. All right, then we gave up on that. So let's take the acid and pick the next strongest base. What's the next strongest base present? Water. And so what we'll do is we'll take acetic acid and react it with water. And this will form hydronium and acetate. And well, this we know that this is Ka. Ka is given 1.8 times 10 minus 5. But we don't just have acid. If this were just an acid solution, right, then that's all we do is Ka. But this is not just an acid solution. We have both acid and base present in significant quantities. So we have to deal with the base. That is, we need a Kb for the base. So the Kb for the base, well, the base is acetate. You know, sodium acetate we call soluble salt. Soluble salts are strong electrolytes. So it's going to split up into sodium ions and acetate. And so the actual base is just acetate and water. And so what we'll do is we're going to generate some acetic acid and hydroxide. So we're generating hydroxide here. And we need the Kb for acetate. Well, the Kb for acetate's no problem. We can figure that out. The Kb for acetate is just equal to Kw divided by the Ka for acetic acid. It's conjugate acid. So we can figure that out. But look carefully at these two. Do I need to do two? These two? No. If you look carefully at these two, what do you see? You should be able to recognize this right off. What do you see? When you look at these two equilibria, what do you see? I'll tell you what I see. I see it right away because I see it right away that do I have to do both of these? No, I don't. Why? I don't have to do both of these because the first one describes the equilibrium between what? The first one describes the equilibrium between acetic acid and acetate in terms of hydronium. The second one describes the same equilibrium in terms of hydroxide. And so basically, they're the same thing. They're the same thing. And this is what's special about the Henderson-Hasselbalch. The Henderson-Hasselbalch is we're down to one, either the Ka or the Kb. Does it really matter which one? No, it doesn't matter. You could do either. And so which one do you think would be more convenient for us if we're interested in the pH? Would it be more convenient to do the Ka, or would it be more convenient to do the Kb? The Ka. And so, for us, you know, we wouldn't bother with the Kb because we'd just be repeating ourselves. In fact, if we solve the Kb, we'd end up in the same place as the Ka, so it's not worth wasting time with that. But you could use either, you know, this one or this one, but not both. Doing both would be a mistake. And so either. We could either do it in terms of pH or pOH. And so let's set up the equation for this here. We have significant quantities of everything. What is significant quantity? Like 0.10 molar is considered a significant quantity of that. But it doesn't, you know, it could be smaller. And so what I'm going to do is I'm going to we have some significant quantity of HAC initial, and we have some significant quantity of acetate initial. And we're going to assume nothing's happened. There's no collision. So we just start off with the significant quantities of both species. And the same thing over here. You know, initial, we have significant quantities of AC minus. We have significant quantities of HAC, but no collisions have occurred. And therefore, that's 0. Water is pure liquid. Well, what's going to happen? In this case, we're going to have minus x plus x plus x. And so here we're going to have HAC minus x, x, and AC minus. X, this is where x is the hydronium ion concentration at equilibrium. Plus x. And so x is equal to the hydronium ion concentration at equilibrium. Well, I can't say it's at this step. I mean, we also have to worry about water, right? Water can add some additional hydronium stuff. Equilibrium just means the final step here, but not total. And so, in other words, what we've got here is Ka is equal to the hydronium ion concentration at equilibrium. You know, the final step, let's say. And I'll just say at the end, rather than call it equilibrium, I'll just call it end of step 1. Times the acetate concentration at the end of step 1, divided by the HAC concentration at the end of step 1. All right, why do I call this step 1? Because there's another hydronium ion producer. What's the other hydronium ion producer? Water. And water's K value is 10 to the minus 14. When we compare the two K values, like here, if I look at the K value here, this is 10 to the minus 5. Step 2 is 10 to the minus 14. Do you think step 2 is going to be a significant contributor or negligible contributor to hydronium? Well, what's the most hydronium we can get from water? What's the most hydronium we can get from water? The most hydronium we can get from water is 10 to the minus 7 molar. In fact, we're probably going to get a lot less than 10 to the minus 7 molar. And so here, what's going to happen is this. Is 10 to the minus 7 molar, when we think about step 2, is 10 to the minus 7 molar significant compared to these numbers? And so we can kind of guess it's maybe not significant. You know, however, if we started off with 10 to the minus 8 molar acetic acid, If we had 10 to the minus 8 molar or 10 to the minus 7 molar acetic acid, then we better start worrying about water. But since we have 0.10 molar and it's a decent acid, then I'm probably not going to worry about water. And so step 2 is KW, but KW should be fairly negligible as far as additional hydronium goes. And so this is what we're going to do here. We're going to do this. You know, this is called the common ion effect here. I already have some product here, so I'm not going to have nearly as much hydrolysis, nearly as much reaction as I normally would. And so what we can say is this. This is going to equal the hydronium ion concentration at the end of step 1. And the acetate ion concentration at the end of step 1 is equal to the acetate concentration initial plus X. Divided by, okay, here, the acetic acid concentration at the end of step 1 is just equal to the acetic acid initial minus X. And then what we'll do is we're going to use a simplifying assumption here. If we use a simplifying assumption, let's write it up here. If we use a simplifying assumption, then we say X is small compared to the initial. And so the X would drop out here and the X would drop out here. And so I end up with this. I end up with the hydronium ion concentration. This is Ka, excuse me. Hydronium ion concentration at the end is equal times the acetate concentration at the beginning divided by the acetic acid concentration at the beginning, initial. Now I'm going to take the log of both sides, in fact the negative log of both sides. So if I take the negative log of the whole thing, then what we'll do is we're going to get this. We're going to get the pKw is equal to the pH, because the negative log of hydronium is a pH. So actually I'll just write it out. The negative log of hydronium at the end of step 1, and we have to make one more assumption. So the negative log of the hydronium, it's up 1, plus the negative log of the acetate to acetic acid. Okay, now this is initial here, initial acetate, initial acetic acid. So let me just continue going down here. Well, what is the negative log of the hydronium? The negative log of the hydronium is just the pH. And then this we're going to leave as is, minus the log of the acetate initial over the acetic acid initial. And then I'm going to solve this for pH. pH is equal to the pKa. pKa plus the log of the acetate to HAC initial. This is called the Henderson-Hasselbalch equation. There are two assumptions that we made. One assumption is that the simplifying assumption works. What's the other assumption that I made? So I made two assumptions in the Henderson-Hasselbalch equation. So one assumption was that the simplifying assumption works. And that's usually a reasonable assumption as long as I have decent or fair concentrations initially. If I had very, very small concentrations initially, then I got to worry about simplifying assumption not being valid. But for buffers, we need significant concentrations. Otherwise, you're making an overly dilute buffer. Do you know what the other assumption is? The other assumption is that I can ignore step 2. How come I can ignore step 2? If I look at that, that's telling me the pH, but I'm missing an important hydronium contributor, and that's step 2. Why can I ignore step 2? Well, I could ignore step 2 because KW is so small, it wouldn't be expected to give much hydronium, and therefore we don't even have to do an ice table. In order to figure out the pH of a buffer solution, I just need the initial values here and the pKa, but the pKa I just get from a book. And so I just need the initial concentrations here. That means I don't have to do the ice table, and so that saves work. We can ignore step 2. Well, I'm assuming I can ignore step 2. And so this is the Henderson-Hasselbalch based on the Ka equation. We can generate the Henderson-Hasselbalch based on the Kb equation as well. You prefer to calculate pOH instead. But like I said, it doesn't matter because pH and pOH are related. And so let's go ahead and generate it here. And so this is going to be minus x plus x plus x. And so this is going to be AC minus x, HAC plus x, and x. X is equal to the hydroxide ion concentration at the end of step 1. This is the initial, this is the initial. All right, Kb is going to equal the HAC concentration at the end of step 1 times the hydroxide concentration at the end of step 1 times divided by the AC minus concentration at the end of step 1. So plugging that in, the HAC concentration at the end of step 1 is the AC concentration initial plus X times the hydroxide concentration at the end of step 1 divided by the AC minus concentration minus X. And then we do the same thing. We do the simplifying assumption, which gives us HAC initial over AC minus initial times the hydroxide ion concentration at the end. And then we take the negative log of both sides. When you take the negative log of both sides, then the negative log of the Kb is called the pKb plus, okay, this would be the negative log of the HAC to AC minus, okay, plus the negative log of the hydroxide. The negative log of hydroxide is the pOH. And so the pOH is equal to pKb plus the log of HAC over AC minus. Okay, both of these are initials, so I don't have to do the Kb table either. And so this is the Henderson-Hasselbalch equation in terms of pOH. But I don't have to solve both of them. I could just solve one, because if I need the pOH, I just take 14 minus the pH. I'll get this same exact number here. So we use one or the other. Typically, we just stick to one, the pH one. And so this is the one we use. We stick to one, but if the base is stronger, if the base is stronger than the acid, then the buffer is going to have a high pH. And so we might have a much stronger base and a weaker acid, and you think we should use the Kb because that's the dominant species, is the base. And the pH of this buffer is high, above 7. Their buffers that go 8, 9, 10, 11, 12, 13, 14. But we still use this because it saves us a step. That way we don't have to do a pH calculation based on that. And so let's take a look at an example. And you can substitute, rather than acetic acid, we can take any generic acid. A generic acid looks the same. It's just called HA rather than HAC. A is the generic anion, and A minus is the generic conjugate base So it'd just be the same equations. And so the Henderson-Hasselbalch for any acid base buffer system is just equal to pH is equal to pKa for the acid component plus the log of the base over the acid. And these are the initial concentrations here. Looks exactly the same. And so if I have this one, I have 0.10 molar HAC and 0.10 molar sodium acetate, then this is easy. I don't even need an ice table. The pH is equal to the pKa of acetic acid, HAC, plus the log of the acetate initial over the HAC initial. The pKa HAC would be the negative log of 1.8 times 10 to the minus 5, plus the log of 0.10 over 0.10. Negative log of 1.8 times 10 to the minus 5 is 4.74. Plus the log of 1 is 0. This equals 474. So that required no ice. We didn't have to do the ice because we're assuming the simplifying assumption works. We didn't do step 2 because we're assuming Kw is a negligible contributor to this. So we can end it there. Now, interesting thing is this. I asked you to make a pH 5 buffer. How do you make a pH 5 buffer? This buffer is pH 474. Now, the way you make a pH 5 buffer is this. You just add a little bit more acetate. If we add a little bit more acetate than acetic acid, then we'll get the pH to go up, pH 5. And then you think, okay, I just keep adding more acetate. I could go to pH 6, I could go to pH 7, I could go to pH 8, just by adding more acetate, right? Well, the problem with that is this. We have something called this is the optimum or ideal pH of this buffer system. The ideal pH is when we have a 50-50 mix. And that means that equal amounts of acid and base component. But, the proper range, we can make a buffer around this pH. We'll just say optimum. But this buffer is capable of making, this buffer system is capable of making buffers in a certain range of pHs. And the range of pHs would be anywhere from 3.74 to 5.74. Go down. If we go lower than 3.74 or higher than 5.74, then what happens is this. What happens is it stops looking like a buffer and starts looking like more of a base solution or acid solution. And that is here. And so if we're at, let's take a look at these numbers here. If we're at a pH of 474, then what we have is we have a 1-to-1 ratio. That is the AC minus to the HAC is equal to 1. It's a 1-to-1 ratio, so 1 over 1 or just 1. If we go to 5.74, then it's going to be the pKa plus 1. In order for log of ratio to be 1, we need it to be a 10-to-1 ratio. And so here the AC minus over the HAC ratio, initial, is 10-to-1. If we went out to 6.74, then actually I should write this over and over again, but do you know what the ratio is if we go to 6.74? That would be pKa plus 2. If we went to pKa plus 2, well, to have the log of what ratio gives us 2? Well, that turns out to be 100 to 1. And so in this case, you know, we could get this all the way up to 6.74 if we have 100 times more acetate than acetic acid. 100 times more means if our acetate were 0.1, then our acetic acid must be 0.001. Is 0.001 a pretty significant quantity? Acetic acid, 0.001 molar or 1 millimolar? No. And so what happens is this ratio, you know, it's heavily biased in base and barely any acid. A buffer should have, you know, significant quantities of both acid and base present. And so if we're at a pH of 374, then we're at a ratio of 1 to 10. 10 parts acid to every one part base. If we go to 274, it's 1 to 100. 174, it's 1 to 1,000. And so, you know, these are two, and so two bias. So we try to keep it within this range here, within a 1 to 10 to 10 to 1 range for the ratio. And so that means when we made up the buffer with a pH 5, pH 5 is no problem, just slightly more acetate than acetic acid. In fact, I could have went to pH 4. pH 4 is no problem here. But pH 3 would be a problem, and pH 6 would be a problem for this buffer system. So now, do buffers work? Well, let's take a look. One thing is buffers should resist dilution, but I'm not sure if that was borne out. Because if I add water to this, will it change the ratio? No, it doesn't change the ratio. If I just add water, it will dilute both components of this. And so one of the things that buffers are supposed to do is they're supposed to give you a stable pH upon dilution. Now, nothing will really give you a totally stable pH, because what's going to happen is if you dilute it to infinity, you know, so it's infinitely dilute, then the pH is going to approach 7 because it's more like pure water. And so if you take a buffer and keep diluting it, pretty soon it's going to look like pure water, because you have so little buffer present. And so, but anyway, it should resist that. And so the higher the concentration, so for example, if we want to 1 molar, then we would say that has a higher capacity. And so if we keep diluting it, then we run into this issue of buffer capacity, which will impact different things. It could impact pH. That is, the pH will start to approach 7, or you're just buying an overly weak buffer. And that is, you know, if I have 0.0001 molar HAC and 0.010 molar sodium acetate, you know, I would look and see, the acetate to acetic acid ratio is 1 to 1. 1 to 1 here, so the pH should be 474. And so this should yield a pH of 474. However, if I went to, let's say, 10 molar acetic acid and 10 molar sodium acetate, I'm going to get the same pH. The pH should be 474. Now, I have to watch out, because pretty soon I'm going to dilute this down so much it's going to be like pure water, so the pH is going to start to climb. Or, you know, the pH should start to approach 7, I should say. It either should drop down for some systems or go up for other systems. For this system, it will go up. And so both of these have the same pH. However, this one's highly concentrated, this one's highly dilute, and so this one's much better. This one's much better resisting pH changes. And so what we're going to do is we're going to do 2 calculations here, 3 calculations. Let's see. Yeah. The 3 calculations we're going to do is this one. And so, do buffers work? Let's see. This is the
question mark. And so let's take 10.0 milliliters of unbuffered, 10.00 milliliters of unbuffered solution. This is just water, pure water. Water doesn't have any buffering action. And so what we're going to do is we're going to add a drop. 1 drop. Should we add?
Well, let's add some strong acid or strong base, it doesn't matter. But let's add 1 drop of 6 molar HCl and see what happens.
So 1 drop of 6.0 molar HCl. Now in chapter 17, there's something new we have to do. One,
You know, we usually use the same strategy. We take the strongest acid and strongest base and react them together. And then the other thing we have to do is solution dilution. And so I've already used step 1 for the first ice table, step 2 for the second ice table. So we'll call this step I. You know, step I is solution dilution. Solution dilution. Solution dilution is the molarity of the dilute stuff is equal to the volume of the concentrated over the volume of the dilute times the molarity of the concentrated. This thing is called your dilution factor. And so the dilution factor is something like this. If I take 1 part of concentrated stuff and dilute it, you know, double the volume, that is, add an equal amount of water, something like that, then it's a 1 to 2 dilution. That would be the dilution factor. And so if I dilute in half, then the concentration is going to be half. So if I take 1 part and dilute it to 3 parts total, it would be 1/3 the original concentration. So we usually look at the dilution factor. And the dilution factor here is going to be significant because 1 drop, do you know about how many milliliters 1 drop is? 1 drop is approximately 0.05 milliliters, but it depends on the surface tension. So we'll just go ahead and use 0.05 milliliters. And so here, I'm going to have this 6 molars being diluted to a total volume. This is 10.05 milliliters, total volume. And so I need to do the solution dilution, so I need to recalculate the HCl concentration. If I recalculate the HCl concentration, then I look at the dilution factor. Dilution factor is 0.05 mils of the concentrated stuff diluted to 10.05 mils times the original concentration, 6.0 molar. And so this is about a 5 to 1,000 dilution. 5 to 1,000 dilution is going to be huge. So let's go ahead and do that. It's like a 5 to 1,005 dilution. So let's just do 5 divided by 1,005. Oops. Times 6. So it's huge dilution. In fact, the diluted HCl concentration now is 0.0298 mole. I'm not allowed to, I'm only allowed 1 sig fig, but I hate carrying just 1 sig fig because it leads to huge rounding errors, which means checking your answers a headache, and so I'd like to carry extra digits for sure. All right, now this. All right, from step 1, this is strong acid. You know, I want to figure out the pH. There are 2 hydronium ion contributors in HCl solution. What are they? Water and the acid. The acid is going to produce, well, this is strong acid, so the acid is going to produce 0.0298 molar hydronium. Should I worry about water? Or skip it? If I get 0.0298 molar hydronium from step 1, because K is very large for HCl, should I worry about water? What's the most hydronium I'm going to get from water? The most hydronium I'm going to get in an acid solution. In fact, I can't even get this much. What is the most hydronium I get from water.
1 to 10 minus 7.
Yeah, 10 to the minus 7. That's the most. I can expect a lot less because of the common ion effect, a Le Chatelier's principle. And so if I'm expecting like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10, 10 to the minus 11 molar hydronium from water, is that going to have any impact on the pH? No. So automatically I'd skip step 2, I'd stop here, and then look at the pH. And so based on this concentration, I would say, no, I'm not going to worry about KW. That's not always the case with HCl. Even though HCl has a very large K, sometimes you have to worry about KW. When did we have to worry about KW? Did you have a chance to review it, any of the earlier calculations, or not yet? When did we have to worry about KW with HCl?
When it was 10 to the minus 8.
Yeah, if the hydronium is 10 to the minus 8 molar, then do we worry about KW? Yes, definitely worry about KW. Because if we're getting 10 to the minus 8, 10 to the minus 9, 10 to the minus 10, it's significant from water. But here it's not, and so what is the pH? It would be the negative log of 0.0298. I left it in my calculator, so I'm going to clear it. 1.52. So the pH is 1.52. This is one sig big thing. 1.52. So did the pH change significantly? Yeah. Now the pH went from 7 to 1.5, so that's 5 or 6 orders of magnitude. So between 100,000 and 1,000,000 times more acidic the water became. All right, now what we're going to do is we're going to do the same thing, except we're going to take 10 milliliters of our buffer solution. Now, it depends on the capacity of the buffer. We could use a high capacity buffer or a very low capacity buffer. It depends on what the situation is, because a higher capacity buffer is going to cost more money. And so what we want is we want enough capacity to handle its intended use. So maybe this is okay if there's nothing in there, nothing is going to be exposed to. But let's just go with our 0.1. We're not going to go overly high, like 10, which would be 100 times more concentrated, or overly low. Actually, this would be like 1,000 times less concentrated. And so let's go with 0.1 and 0.1. This will be 0.1 molar HAC. Actually, you know what? This is not a fair comparison. It's not a fair comparison because our water should have started at a pH of 7. The water started out at a pH of 7 and ends at a pH of 1.5. So that's like 5 or 6 powers of 10. That is more concentrated. So, I don't think this is fair. Even if we start at a pH of 5, I still don't think it's fair. We could start at a pH of 5, and in fact, I can calculate it. I can get this to pH 5, no problem. If I wanted to figure out how I could get this to pH 5, I just have to figure out what the ratio that's required. Because if I want the pH of 5, for example, let's just do this as an aside. I would just do this. My desired pH is 5.00, and this is equal to the pKa, which is known, 4.744, plus the log of the ratio. And so all I have to do is solve for the ratio of acetate to HAC initial, and then I just get that. And it turns out the ratio is just slightly, in fact, let me get it. So acetate to HAC ratio is gonna be 5 minus 4744, 5 minus 4744 equals 0.256, and then take the anti-log of that. Anti-log, here it is. And so I just need a ratio of 1.80. See how many sig figs. Oh, just carry some extras. 1.80 to 1. And so, you know, it's about a 2-to-1 ratio. Acid to base. 2-to-1 ratio, that's still okay. It's significant. It's when we get to 100 to 1, then we start to worry. You know, but as long as we keep it to 1 to 10 and 10 to 1 range, then we're okay. So 2 to 1 roughly is okay. Or 1.8 to 1 is okay. And that'll get me to pH 5, but I want to go all the way to pH 7. If I go all the way to pH 7, then do you know what the ratio is going to be? Well, that's going to be about 2 to 3 units. So let's say it's 3 units up, or 474, no, 2 units up. If it's 2 units up, then rather than having a plus a little bit here, we only needed to go plus 0.24. We need to go plus 2.24. And so let's go ahead here and then look. If I wanted a pH 7, just to keep things fair here, and I'm going to use this buffer system, then what's the, let's leave it aside. I'll give you another aside calculation. So I want a pH of 7.00 now. So I want to start at the same pH as pure water, although your water wasn't 7.00, was it? What was your water? Yeah. It was like 5, and then DI water is pretty acidic. But anyway, let's say we're starting off with pure distilled water. I mean, just distilled water, freshly distilled. It should be pH 7. And so, you know, it's going to be the pKa 7.4 plus the log of the ratio. And so we just solve for the ratio. And the ratio is going to equal. All right, 7 minus 474 is going to give us 2.256. 2.256. We'll just 10 to that. 10 to 2.5256. I gotta be a little bit more careful. This is 180. 3, 1. I should have been able to figure it out based on this. Did I screw that up? Yeah, you know what? I still screwed. Shoot. Where did I get this 2.56 from? That's the problem with doing it with calculations without even thinking. You know, this is why sometimes I like to do it in my head. But that was supposed to be 5 minus 4.74. I must have miskeyed it in my calculator. Yeah, I did. 5, but you know, it's okay because I left the digits in my calculator. This was supposed to be 0.2. Sorry, 5, 6. pKa is 4744. All right, so here we got this 180 to 1. 180 to 1 means if my acid, if the acid is 0.1 molar, then the base must be what? Well, if the acid is 0.1 molar, and this is my ratio here, there's 180.3 parts of base for every 1 part of acid. And so I have 0.1 molar acid, and then the ratio is going to be like this. It's going to be 180.3 molar base to every 1 molar acid. Then I have to make the base 18.03 molar. 18.03 molar. And so, well, okay, this is 10 milliliters. 10 milliliters is going to be 0.0100 liters times 18.03 moles per liter of base sodium acetate. The sodium acetate we're using was the trihydrate, which is about 138 grams per mole. It depends on which sodium acetate you use. It could be the anhydrous stuff, which is going to have a different molar mass. So that's 0.01 times 18.03 times 138. 24. And so we have to dissolve 24.88 grams of sodium acetate trihydrate in 10 milliliters of water. Is that going to be easy to do? 24.88 grams. You know, we might not be able to get it all to dissolve because this might exceed the solubility of this. And so what we'd have to do is we'd have to go way lower here. If we go way lower here, then that means the acid is going to go way lower. And so, for example, if we made the acid concentration variable and fixed the base concentration, let's say if we made the base 0.1 molar, then the acid's got to be 1,000 times, or not, is it 1,000? No, 200 times or so more dilute. And so it's going to be 0.001, something like that. And so, you know, the base is going to, the acid is going to get quite low in terms of concentration. So this is not practical. It's not practical because this buffer would be heavily biased in base. It would have a huge base to acid ratio. And so it's not practical. We don't want the ratio to go beyond what? We try to keep the ratio within one limit. You know, this ratio is getting too big, 180 to 1. It's way too big. We try to keep the ratio between what and what. Yeah, Renee?
I think it's
1 to 10 to 10 to 1. You know, we try to keep it within that range. So this is not going to work. This acetic acid, sodium acetate, which we call a buffer system, this buffer system is not good for making pH 7 buffer. And so we need to find a buffer system that's good at making a pH 7 buffer. So what would we look for in terms of that? And
Slightly stronger base, maybe?
slightly stronger base? Okay. We could do that, but we would look for a pKa of what or a Ka of what? If we want a buffer of pH 7, then we would look for a pKa between what and what? Yes, exactly. That's good. We'd look for a pKa between 6 and 7, which means we look for a Ka, because pKa is the negative power, so we'd look for a Ka between 10 to the minus 5 and 10 to the minus 1 times 10 to the minus 5 to 1 times 10 to the minus. Wait, sorry, not minus 5. That's wrong. What would it be? Yeah, yeah. 10 to the minus 6 to 1 times 10 to the minus 7. We go up to this chart over here and look, what would be suitable to use. Or we look in pencil D, to C. What was that as far as options go? And so let's go to D. I spent too much time talking right now. I need to talk about tomorrow's lab. All right, what lab are we doing tomorrow? pH titration. This is not happening. To be continued. We'll talk more about buffers next time. So we're going to continue this. After buffers in chapter 17 comes titrations. So let's take a look at a typical titration curve. In a pH titration, we monitor the pH. So let's plot it on the y-axis here, versus milliliters of titrant. And so in a normal titration, we're only interested in one data point. In a normal titration, we just want the end point of the titration. That's where the indicator changes color, like phenolphthalein or something like that. In a pH titration, though, we're going to monitor this throughout. And not only that, once we hit the end point, we're going to keep going well beyond the end point. And so we don't stop when the indicator changes color. We keep going another 5-10 milliliters beyond that. But all the while, we're going to be checking on the pH here. So let's take a look at a couple of curves here. Draw these the board. All right, and so this is what a titration curve looks like. Oops, right there. Curve because. So here's the pH plotted on the y. Here's the milliliters. And you see how they're monitoring it? In a normal titration, we stop here. And this is where actually we stop here. This is where phenolphthalein starts to turn pink, is right here. In this particular titration, we should have stopped here, which is the equivalence point. The equivalence point at the end point, they're off. You can see that there's going to be a little error. We should have stopped here. In fact, we should use bromethionol blue as the indicator because what the color bars you see here are how the indicator changes color. Phenolphthalein is going to be colorless all the way at pH is below 9. Above pH of about 9, it starts to go pink here. If we use bromethymol blue, it's yellow in acidic solution, and then it's blue in basic solution. So yellow and blue make green. But green's hard to detect, and so even though bromethymol blue would give us the equivalence point in this particular titration, which is strong acid and strong base, it's, for a lot of people it's hard to see. And so it's much easier to see this one here. Now, this is the curve, so what we want to do is we want to continuously monitor pH. And what kind of resolution can we get in continuously monitoring the pH? We could get 1 drop resolution because you could go drop by drop. Do you see? This looks continuous. It looks like they collected data at infinitesimally small intervals, right? This looks totally continuous, but it's not really continuous. In a curve like this, you know, we collect data at intervals. And so if we did drop by drop intervals, we would actually have a gap between the data points, you know, where we don't have data. But as long as we collect a lot of data here, we aren't going to miss anything. But the highest resolution we can have is 1 drop. But do you know how many drops there are in a milliliter, roughly? 20 drops in a milliliter. So if we go out to 50 milliliters, how many drops is that? Well, that's 50 times 20 drops. So it would be 1,000. What is that? 50 times 20 is 1,000. Yeah. 1,000 drops. How long would that take? Because what happens is you add a drop, and then you have to stir it and wait until the pH stabilizes and then take the reading. So if you had to take 1,000, how many pH readings did you take the other day? 7? I think there were 7 solutions. Can you imagine taking 1,000 readings? How long would that take you? Well, let's say you could do 1 reading every 20, 30 seconds. If you did 1 reading every 30 seconds, then 1,000 readings would be 500. 500 minutes. 500 minutes would be, well, we have 3 hours. So if we have 3 hours, and so we need to do 1,000 drops, 1,000 readings over 3 hours. 3 hours, well, you got to take away about 1 hour getting set up. So 2 hours. 2 hours would be 120 minutes. So 1,000 readings in 120 minutes means we have to do 8 readings per minute. 8 readings per minute, which would mean we'd have to do a reading in less than 10 seconds, without any stops. And so we, you know, basically it's impossible. We can't get this kind of resolution, unfortunately. This is great because this looks pretty continuous. And so what kind of resolution can we get? Well, what would be more reasonable? Rather than taking a reading like every 8 seconds or something like that, it'd probably be more reasonable to take a reading every 30 seconds or every 20 seconds or something like that. And so that's going to mean this. It's going to mean that we need to spread out the interval. Otherwise, we don't have enough time. The problem is that if we spread out the interval, we might miss something. So, for example, I don't have time, so spread out the interval to, let's say, 0.5 milliliter or something, or milliliter between. If we do that, then we lose, we don't see where this went up, because it looks like the pH shoots up near the equivalence of the endpoint. And so we don't know if the pH shot up here, or shot up here, or somewhere in between, And so this, this means this. Where the pH titration curve is fairly flat, we try to spread out the data. Where it starts doing something, we try to collect data at 1 drop intervals. Because we want high resolution here. Well, that's one curve. The curve might look like this. Well, curve might look like this. Here, so here we kind of spread it out a little bit, but when we get to this structural feature here, we want to go drop by drop. A curve might look like this. And so what we have to do is we have to anticipate something like this happening. We have to anticipate collecting data at very fine intervals here and here. But how do we predict where this is going to happen? Because you know what we're titrating? We're titrating an unknown acid. Because unknown acid, how do we know when to slow down? Well, one thing you could do is you could keep an eye on the pH. You can keep an eye on the pH, and as the pH starts to rise, you better slow down. But it looks like it's rising here. But then there's going to be a steeper rise, steeper rise. And so if you start seeing a steeper rise, you better slow down because you might miss this. Every semester, somebody misses it, one group. Misses it, sometimes more than one group. And so you got to slow down. Now, the thing for this is, even though it's an unknown acid, we don't know if it's monoprotic or diprotic. This happens to be a diprotic acid. We see two equivalence points like this. Monoprotic, we just see one steep rise. We don't know if it's monoprotic or diprotic, so we have to just assume it's diprotic and then collect data so that we can cover this. And so what we're going to do is we're going to do two titrations tomorrow. One, we're going to do a standard titration. It turns out that for diprotic acid, the second hump here is usually in the pH range above 7. And so phenolphthalein works pretty decent for catching the second one. And so phenolphthalein will be colorless and then will turn pink here for diprotic. That means if we have a diprotic acid, then we better slow down halfway. It turns out about halfway here, we better slow down. If it's monoprotic, then for weak acid, the first equivalence point is here. And so if we slow down for monoprotic, it'll just be flat here, but we got to slow it down here. So we're going to slow down in this range and this range. Well, how do we know where to slow down? We're going to do a quick titration first with phenolphthalein without monitoring the pH. And then we're going to figure out where this is. And then in this range, we're going to start slowing down before and after. And then halfway here, we're going to start slowing down before and after. So we catch a lot of data here and a lot of data here. And the other parts, we can spread out the intervals so we have enough time to finish the lab. All right, let's stop here. We'll talk more about it tomorrow. But there's no handout. This is just data collection.